All right, cool. Yeah, so thanks. This is joint work with Fuyuki Kitagawa, Ryo Nishimaki, and Takashi Yamakawa. And let me start by just giving some background on the classical notion of obfuscation. Right, so an obfuscator is basically a one-way compiler. So it's a program that takes as input the description of a circuit and outputs an obfuscated circuit, and it's supposed to maintain the functionality of the program. So it's a compiler, but it's one way in the sense that it's supposed to like kind of scramble all the implementation details of the circuit C. So just given the obfuscated version of C, you can't kind of reverse engineer and learn how C was originally implemented. And its most basic applications are just exactly for like software protection, right? So it's useful for protecting against reverse engineering, intellectual property theft. It's like an anti-piracy tool. But over the past decade, basically, it's been a huge topic in cryptography because at least this particular notion called indistinguishability obfuscation has been shown to be like extremely useful across like a broad range of applications in crypto. For example, towards constructing fully homomorphic encryption, other advanced forms of encryption, and even some nice applications in a quantum world like public key quantum money. Along with all of this work, it was another parallel line of research on constructing this classical notion of obfuscation. And by now we have good constructions, but from some pre-quantum assumptions, and there's also like an ongoing line of work constructing post-quantum candidates. So suffice to say, like obfuscation has been a really major topic in crypto over the past like 10 years. This talk is going to be about the quantum analog of that. So it's basically just a question of can we construct a one-way compiler for quantum computation? And so there's a lot less that's known about this. I'll mention a few works. So there's this work of Alajic and Pfefferman from a few years ago that gives kind of more or less introduces the topic, gives a bunch of definitions, some possibilities and applications, and I think asks for further work on the topic. In terms of constructions of obfuscation for quantum circuits, there hasn't been that much prior to this work. There's a few works that address like perfectly secure obfuscation for kind of necessarily limited classes of circuits. In the computational setting, this work of Broadbent and Cosme also shows how to obfuscate circuits like almost Clifford circuits. So there are circuits with just a logarithmic number of non-Clifford gates, and they assume post-quantum I/O for that. And then there's another work of myself and Giulia Malavolta a couple years ago where we show how to obfuscate null quantum circuits, which are quantum circuits that always, on every input, just outputs 0. We give some cryptographic applications of that, and we do this in the classical oracle model, which I'm going to explain in a little bit. But the point here is that this question has basically remained pretty open over the past few years. Is it possible to obfuscate general purpose quantum computation? So this work takes a step forward. Our main result is to show that we can obfuscate pseudo-deterministic quantum circuits in the classical oracle model, also under the assumption of learning with errors. So let me explain what this result means. A pseudo-deterministic quantum circuit is one that takes classical inputs and produces classical outputs. And it's just kind of, if you're familiar with pseudo-deterministic classical circuits, it's basically the same thing. For each input x, there exists some output y that it will output with overwhelming probability. Okay, and in terms of like pseudo-deterministic quantum circuits, the most prominent example has to be just a circuit that implements Shor's algorithm for factoring or finding discrete logs. So now let me explain more of like the syntax of our results. So what we show is this Q-off procedure that takes as input the description of a quantum circuit Q, and its output actually has two parts. One part is going to be a quantum state, and the other part is going to be a classically obfuscated classical program. So we're going to make use of classical obfuscation to do this. And then there's this corresponding evaluation procedure, right? That if it has the quantum state and the classically obfuscated program and some input x, they can learn what Q of x is, and they can kind of repeat this on different inputs of their choice. But for security, this is where the classical oracle model comes in. This is what we can manage to prove. So if I model the classical obfuscation as implementing essentially a black box, then what we can show is that any adversary that's kind of given the quantum state And black box access to F can be simulated by a simulator that's just given black box access to the functionality Q. Okay. So this is essentially a black box. What we show is a black box obfuscation of Q in the classical oracle model, where we're assuming that the adversary only has black box access to the classical oracle for F. Okay. So, as it stands, this is like just kind of an oracle result, and if you like that, can be meaningful. But we also know that there are impossibilities for actually, translating, like realizing black box obfuscation just in the plane model or in the real world. And so the best thing that we can say for this is to say, well, if we instantiate our classical oracle with a post-quantum indistinguishability obfuscator, we can conjecture that the resulting scheme is an indistinguishability obfuscator for Q. We don't know how to prove this, but I would say that our oracle model proof gives some evidence that this is true. And you can regard this as basically a candidate. So this is something that remains open, but prior to our work, we didn't have any candidates or heuristic results of this nature. Okay. So, most of this paper is concerned with the construction. We also give some initial applications of this notion. We can construct functional encryption for this class of circuits. And we can also, we also show how to construct copy protection for this class of circuits. Copy protection is this kind of like quantum specific anti-piracy notion, which has traditionally been studied to apply to classical functionalities. And so we show that, we can, and it might be interesting to study copy protection also of quantum functionalities as well. Okay. So now let me get a little bit more into the high-level details, the technical details. So the starting point for our construction is quantum fully homomorphic encryption, in particular the scheme due to Mahadev in 2018. So what does this allow us to do? So if I encrypt the description of my circuit Q, and I have a ciphertext that encrypts Q, then I can take any input I want, and I can run some like homomorphic evaluation procedure on that ciphertext to get an encryption of Q of X. Okay, so this is kind of almost an obfuscation scheme, except that I'm able to produce encryptions of the outputs instead of the outputs in the clear. So I want to give you some way of actually obtaining the output. Of course, I can't just give you the secret key of the fully homomorphic encryption scheme, because that would also allow you to decrypt your original encryption of Q and learn the description of Q, which is exactly what we're trying to hide. So I need to come up with a different way of doing this. And this suggests the following approach, which is if I want to obfuscate Q, I will give you an encryption of Q, and then I'll also give you this like classically obfuscated program that has the secret key hard-coded into it and will only allow me to decrypt kind of honest evaluations of the circuit. And so this like var then decrypt circuit will look roughly like this. It will take X, an output ciphertext, and some proof as input. It will check that this proof shows that this output ciphertext was computed honestly, and only then will it actually decrypt the output ciphertext using the secret key. So this is hopefully some way to guarantee that we'll only be able to decrypt output ciphertexts that were generated honestly. Okay. So this is the template we want to follow. In order to instantiate this, what we're going to build is something that we call publicly verifiable quantum fully homomorphic encryption. And so this is like a standard QFHE scheme, except for a couple differences. So one is our encryption algorithm will also output some verification key. The evaluation algorithm will take as input a ciphertext, some X, and it will output an evaluated ciphertext along with a proof that it evaluated this honestly. And then there's this extra verification algorithm, which will check the proof, right? And so basically our soundness notion, first I should say that it's very crucial here that our verification algorithm here is classical, because this is exactly what is going to be part of our obfuscated program, and we only want to assume classical obfuscation, right? So we need kind of a classical, publicly verifiable QFHE scheme, where soundness basically says that if I'm an adversary and I get the verification key and some ciphertext and I produce X, an evaluated ciphertext and a proof, then if I can make the verification algorithm accept, then it must be the case that this output ciphertext is a valid encryption of Q of X, right? So this is what we want, and this is what we build in this work, at least in the Oracle model. If you're familiar with prior work, there might be like a couple things that come to mind. So there is this work of Alogix et al. That constructs verifiable quantum FHE. There's also this work, Mahadev, that constructs classical verification of quantum computation. And recall that like this is exactly kind of what we're trying to do, right? We want this verification algorithm to be classical, and it's checking the correctness of this quantum evaluation computation, right? So there's a few issues with using these prior techniques. So first, this verifiable QFHE scheme, verification for this scheme actually requires you to know the QFHE secret key. And this is a problem for us because we want to like kind of obfuscate this algorithm and give it to an adversary. And potentially if the adversary can kind of query this algorithm multiple times, they might then be able to learn the QFHE secret key, which would break our security. So we would ideally like verification not to depend on the secret key. And then Mahadev's scheme also suffers, like, if we just apply it on top of QFHE, like it won't need the secret key, but it suffers from a similar issue where you still need a private verification key to verify in her scheme. And it's not reusably sound in the sense that, again, if I obfuscate the verifier and I query the verifier many times, you can show that you can actually learn what that verification key is and then use it to break soundness. There's another issue with Mahadev's scheme is that it only applies to pseudo-deterministic quantum computation, or BQP. Although recall that the only thing that we're trying to obfuscate is pseudo-deterministic computation. The problem is that the quantum computation that we're trying to verify is actually a sampling circuit. Okay, so this like QFHE evaluation procedure actually outputs like a sample from a distribution. And we don't really know how to, or at least her protocol was not built for verifying such computation. There is a follow-up work, Chung, Li, Lin, and Wu, that construct classical verification for sampling problems, but their soundness is 1 over poly. This is also an issue for us because this means that after like polynomially many queries, the prover will actually be able to break soundness. And I will say that actually improving this final thing here to like negligible soundness, I think is a great open problem, but it's not something that we address in this work. In my last couple of minutes, let me give you a taste of basically the high-level approach that we take in this work. And so recall that what we want is, suppose I'm a QFHE evaluator. I have my input ciphertext and my X, and I'm going to interact with a classical oracle to produce an output ciphertext along with a proof pi that anyone can check is valid. And so I'll do this in 3 steps. First, I will take the QFHE computation, kind of like run it coherently, basically, and I'll let phi x be the history state of this computation, okay? And actually, I'm going to kind of prepare like many copies of this history state, and then I'll commit to them using what we call a polyfunctional commitment scheme. And the result of this commitment scheme will just be a classical string that I can send to my classical oracle. At this point, the evaluator and the oracle will interact to run what's called a measurement protocol, which is first described by Mahadev. We use some ideas from her work and some follow-ups on the copies of psi x. And the result of this measurement protocol is that the oracle obtains from some of the copies of the history state some like results of local Hamiltonian measurements. And from other copies, it will obtain like some samples of the output. Okay, so it's going to obtain kind of multiple measurements and multiple output samples. Finally, the oracle will run the Hamiltonian verifier. If it accepts, it will take all the output samples, and it will be fairly convinced that like most of these output samples are honest. Maybe not all of them, but most of them will be pretty good. So it will just kind of run a majority function under the FHE to produce one final ciphertext that it returns to the evaluator. And the proof is just going to be this classical transcriptive communication between the evaluator and the oracle. Okay. So that was a quick run through. Let me say, before I conclude, just a few more words about what is this polyfunctional commitment? Why do we need it? This commitment scheme is a way to classically commit to a quantum state that supports, after committing, it supports opening the committed state to either standard or Hadamard basis measurements. And we need to like open these history states to these measurements to make step 2 work. And it's also crucial for our security. This initial step where we kind of commit to the states first is what we use to overcome the issue that, like, as I mentioned earlier, this Mahadev style measurement protocol is not reusably sound. Okay, so this is kind of the step where we kind of boost from non-reusable soundness to soundness in this setting. And a big kind of technical part of our work is to address this third issue, is that actually this commitment scheme, we need it to be publicly decodable in some sense. There's this prior work of Brikersky et al. That basically constructs polyfunctional commitments, but they're not publicly decodable. And we extend their framework to work with high-dimensional coset states and obtain public decodability in this way. Okay, so let me quickly mention some open questions. One thing I haven't mentioned yet is actually the commitment key for our polyfunctional commitment scheme is a quantum state. And this is actually the quantum part of our obfuscated program. But it's not inherent that we would need a quantum obfuscated program. So can we make this commitment key classical, and can we make our obfuscated program completely classical? And of course, a natural question is, can we, we prove all of this in kind of an oracle setting. Can we prove security just from indistinguishability obfuscation? This is a great question. And then finally, natural question, can we go beyond pseudo-deterministic quantum circuits? Can we obfuscate sampling circuits, that output like a sample from a classical distribution? And can we obfuscate more general, families of like quantum maps from like quantum inputs to quantum outputs? Okay, and so I'll stop there. So thanks.
Okay, so thanks, James. Questions?
So can you say a bit in the application to copy protection? Like what would be the result, final result in terms of copy protection?
Yeah, it's a pretty direct extension of this result of this, if you're familiar with like the Aronson et al. Copy protection paper, where they show that like assuming a classical oracle, you can copy protect any like unlearnable classical circuit, basically. And so we extend that to just unlearnable quantum function, pseudo-deterministic quantum functionalities.
So this classical oracle that you need is this FQ, right? So does it depend on the class that you are trying to copy protect?
Yeah.
I see. So
yeah, just like they also kind of they're using classical obfuscation in their result, right? And so we're saying, well, if we can plug in like quantum obfuscation where they had used classical obfuscation to extend their class of programs.
So okay, so like if you can obfuscate these functions classically, then like any such function classically, the kind of you consider, then you can have. I see. Okay.
Yeah.
Other questions? So if you had a protocol for SAMP BQP verification with negligible soundness, would that sort of immediately get you some upgrades, or would you still have
probably
to do a lot
not
of work?
immediately. It might be like a useful step, but like there's always the problem of like maybe it's like privately verifiable, or maybe it's like highly interactive, and like usually those type of protocols wouldn't like immediately give an obfuscation scheme. Yeah.
Okay, one more, sorry. So you said that you have a reason to believe, if I remember, if I'm not rephrasing you too badly, that you have a reason to believe that this same construction should work if you plug in I/O. Can you say a little bit about why?
I don't know.
Why you believe that?
Reason to believe. I mean, there's no reason like to believe, or like I don't have any reason to believe that it's like suddenly like broken if we use I/O. I think there's a lot of like it seems to require some like new techniques for like dealing with I/O, or like maybe, like I'm just not sure, but I don't see any reason why it would suddenly be broken if we just use I/O. Yeah.
These classical like switching proofs.
Yeah.
They just don't.
Yeah. There's a couple components of the security proof where I think we like really use the oracle, and so I'm not sure how to replace that with I/O. Yeah.
Okay, great. Let's thank James again.